All right, so let's talk about classification of matter. All right, so this should be a fairly straightforward review of things that you've learned in your early science courses. Um, you can classify matter by physical state, and physical state simply means whether it's a solid, liquid, or gas. Okay, and intuitively we know the distinction between these. So, oops, sorry, I forgot to share my screen. Okay, yes, I am recording it. Okay, all right, so, okay, can you see it now? Okay, good. All right, so classifying matter, like I said, instinctively we know the distinction between solid, liquid, and gas. So we know that an ice cube is a solid, a rock is a solid, water is a liquid, wine is a liquid, sugar is a solid, air is a gas, steam it's a gas, helium's a gas, that's what you fill your balloon with, gasoline, gas is a liquid, and neon is a gas. And that's neon is the gas that you put in your neon lamps. All right. So we know intuitively the differences, but how are they really different? One way you can differentiate between these three physical states is by describing the volume and the shape. Okay, so we say that a solid has a fixed, solids and liquids have a more or less fixed volume. In other words, the amount of space they occupy is more or less fixed, whereas a gas fills up whatever container you put it in. So the volume of the gas depends on where you put it. Okay. As far as shape is concerned, liquids and gases have a common characteristic in that they tend to follow the shape of the container. Liquids in particular will just follow the shape of the bottom of whatever container you put it in, whereas the gas, since it fills up the entire container, the shape of your gas sample would be whatever the shape of the container is. Solids, on the other hand, tend to hold its shape. Okay, so the ability of liquid, the inability of liquids and gas to hold their own shape is gives them because gas and liquids follow the shape of their container. We refer to them as fluids. Okay, so that's what they have in common. And solids and liquids, what they have in common is they have a fixed volume. All right. So at the molecular level, oops, not yet. Okay, phase changes. Some terminologies here. A phase change, another word for physical state is a phase. So what we call a phase change is simply a change of physical state. So if something goes from a solid to a liquid, we say it melts. Okay, so that process is called melting or fusion. The opposite, liquid to solid, is freezing. Vaporization is conversion of a liquid to a gas. The opposite of that, gas to liquid, is condensation. Solid changing directly to a gas without first melting is called sublimation, and then changing of a gas directly into a solid without turning into a liquid first is called deposition. Okay. One characteristic of melting, vaporization, and sublimation as you go from solid to liquid to gas. Okay. These processes are what we would call endothermic. They require heat. So usually we use a triangle underneath an arrow to indicate a change that is accompanied by heating. Okay. And the opposite, going from gas to liquid to solid, would be that would be your condensation and your freezing. Those are exothermic. For those to happen, heat has to leave your system. Okay. So those are just some simple terminologies. So let's see if we can apply those terminologies for these. What phase change is involved when a mothball disappears? That would be what? Sublimation. Good. That's a solid. It just gets smaller and smaller all the time, and that's your solid turning directly into a gas. And one way you can tell it's turning into a gas is you can actually smell the gas. Okay, so you can smell the mothball. Those are molecules in the mothball that are going to the gas phase. They go inside your nose. Okay, and here's your nose right here. Here's your eyes, and then sends it goes into your nose, and nerve endings in your nose sends a signal to your brain that tells you that something hitting it. Okay. Uh, Ice turning into liquid water, that's melting, right? That's solid turning to liquid. Water droplets forming on the outside of a cold glass of water, what would you call that? So I've got some ice and I've got some liquid water forming on the outside. Condensation, right? So that's gas turning into a liquid. How about ice shrinking in a frost-free freezer? Yes, it's vaporization. It's turning into a vapor, but in this particular case, you have a solid changing directly into a vapor. So vaporization normally is reserved for transformation from liquid to a gas. So this would be sublimation. Okay. What you have in your freezer is you have solid ice, solid water in equilibrium with water vapor, and your freezer keeps taking away that water vapor, and so what happens is molecules of water from your ice goes into the gas phase directly without melting. So that is sublimation. In fact, if you're familiar with the TV show called Arthur on PBS, at one time, Arthur's baby sister, TW, put a snowball in the freezer, and the snowball disappeared. And that's probably what happened, sublimation. How about sweat disappearing from your skin? That's evaporation or vaporization. Okay. All right, so why do you feel cold when you come in drenched from the rain? So you're wet, right? So you've got water on your skin, and so what happens? As the water evaporates, that's an endothermic process, okay? So this is an endothermic process. That means the water absorbs the heat, and where does that heat come from? From your body, and so you feel cold. Okay. Why is exposure to steam more dangerous than exposure to boiling water? Well, the reason for that is when water vapor in the form of steam at 100 degrees Celsius turns to liquid water at 100 degrees, boiling water at 100 degrees. This is a gas to liquid, that's a condensation. Okay, this is a process that liberates a lot of heat, so this is an exothermic process. And so, in fact, this process alone, the condensation of steam into boiling water, generates about 8 to 9 times more heat than boiling water just cooling down to to body temperature. All right. Now, let's look at the atomic interpretation of phase changes. So, how do we interpret phase changes? Well, we say that matter is made up of particles, atoms, ions, and molecules. Okay. And you can explain phase changes as follows. If your particles, like your atoms, are very far apart, then they move more or less independently. What do we mean by very far apart? That means they're separated by a distance of at least 1 nanometer. So when we say far apart, that's really very short distance on the atomic scale. But any distance that's about greater than 1 nanometer might be considered far apart. If you recall, when we had our potential energy of interaction last time, so this is distant. Let's see. Okay. If you were to plot potential energy versus distance, all right, you're pretty much over here in this region where the potential energy has leveled off when you're beyond 1 nanometer. Okay, so at intermediate distances or at very close distances, very short distances, less than 0.1 nanometers, you're in this region right here. You have repulsions between the positively charged nuclei as well as among the electrons. You're crowding all of those charged particles in a very small area. Okay, so if you remember, this is a plot of potential energy versus distance. Distance is the x-axis, potential energy is the y-axis. Now, at intermediate distances, typically between 0.1 to 1 nanometer, okay, then you have attractive forces among the atoms and molecules. These we can use to explain phase changes. Okay. Now the idea is if you're heating something, okay, that simply means you're giving your particles more kinetic energy, and so they're better able to overcome the forces of attraction between them. If you remember last time we said that if two particles are stuck together, in other words, they're very close to each other, then that suggests that they are at the bottom, trapped in what we call a potential well. Okay, so if they gain kinetic energy from a third body, that allows them to spread out and to separate from each other. Okay, and so the way they gain kinetic energy is by collisions with other molecules. And so if you're putting it in contact with something hot, you're giving them energy to be able to separate. So what that suggests then is in the gas phase, your particles are far apart, whereas in a solid or liquid phase, they're as close as possible to each other. Okay. So exactly how far apart are they in a gas? Here's a typical scenario. If you have a 25 or 24.8 liter sample of air at room temperature, it's going to contain 602 billion trillion molecules, 6.02 times 10 to the 23rd molecules. What's the average distance between these molecules? Well, imagine you have a 24.8 liter box, okay? And so this is 24.8. Let's divide this into little cubes. 600 billion trillion cubes. So divide that by 600 billion trillion cubes. Let me see. Let's divide 24.8 liters by 6.02 times 10 to the 23rd molecules. Okay, a liter is, let's make that milliliters. So let's change that to milliliters. So 24.8 liters. Let me change that to milliliters. So 1 liter is 1,000 milliliters, which is the same thing as a cubic centimeter. I'm just changing my units here. So if you divide that volume by the number of molecules, you get more or less the volume per particle or per molecule. So what would that number be? Let me pull up my calculator here. I have 24.8 times 1,000 divided by 6 times 10 to the 23rd. You're looking at about 4.1 times 10 to the negative 20. 4.13 times 10 to the negative 20 cubic centimeters. So you can, if you can imagine the molecules are spread out as much as possible here. Okay, they're spread out. So each cube has one molecule. Each of these little cubes has one molecule. So each of these 600 billion trillion cubes as one molecule, then you can say the size of the cube that's occupied in quotes because it's not really fully occupied by a molecule would be the cube root of this. So this the rad the side, the length of the side of that cube is going to be the cube root of 4.13 times 10 to the negative 20 cubic centimeters. So if you take the cube root of that, so I'm going to raise that to the power 1/3. I've got a cube root right here. That gives me 3.45 times 10 to the negative 7. So about 3.5 times 10 to the negative 7 centimeters. Okay. So, or in terms of meters, that's going to be 3.5 times 10 to the negative 9 meters. So, oops, I can't seem to hold this thing. So that's 3.5 times 10 to the negative 9 meter, or 3.5 nanometers. Okay? So in other words, the average distance between, the molecules here are going to be moving, are going to be continuously moving, but on average, the distance between molecules in a gas, in air, is 3.5 nanometers. Okay? Remember we said earlier, if they're about more than 1 nanometer apart, they're going to be moving more or less independently of each other, so they're not going to be attracted to each other. There's going to be minimal interaction between them on average. Compare that to a typical size of a molecule, which is 0.16 nanometers. So how does 3.5 compare to 0.16? Well, 3.5 divided by 0.16 is 21, so about 22 times larger. What that means is, okay, if I have one air molecule over here, okay, and the diameter of that is about 0.16 nanometer, okay, 20 times that distance, okay, so 20 times 0.16 nanometers is where I'll find the next molecule. There's a lot of empty space in between them. Okay, so the molecules in air are very, very far apart from each other. By when we say very, very far apart, we're talking about on average about 3.5 nanometers. Okay, on an atomic scale, that's a huge number. Even though from our perspective, that's a very small number, but we're dealing with very small things here. Okay, so that's how far apart they are in a gas. Now, in a water sample, a liquid sample of water, for example, if you have 18 milliliters of liquid water, okay, so that's 18 cubic centimeters of water, you have the same number of molecules. So you can see 18 versus 24.8 liters. This 24.8 liters is 24,800 milliliters, okay? Whereas if all of those molecules, you can shrink them into a liquid, okay, then they'll only occupy 18 mils. They're much closer together, and if you calculate the average distance between the molecules in water, they're only about 0.3 nanometers apart. So between water molecules, the distance is about 0.3 nanometers. Okay? Each water molecule is about 0.15 nanometer in diameter. So you can see they're as close as they can be in a liquid or a solid. It's very hard to squeeze those molecules any closer to each other. So we're saying then in a solid or a liquid, your atoms are as close as they can be. If you push them any closer together, they start to repel very strongly, so you can't get them you can't squeeze them. Okay, whereas in a gas, the molecules are so much farther apart. They're about 20 times at room temperature. The distance between typical molecules would be 20 times their actual size. So there's a lot of room for them to move about. All right. So why are solids incompressible then? They're hard to squeeze to a smaller volume. The reason is they're as packed, as close together as possible. Squeezing them further will just be opposed by strong repulsions among the nuclei and even among the electrons themselves. Why do they have fixed shape? Because they simply don't have enough energy to move apart. If you give them enough energy, they'll be able to move more. They'll be able to overcome those forces of attraction. In other words, you could say that they're trapped in that potential well. Okay, down here, they're as close as possible. So they do move. They still do move. Their movement is limited to small vibrations, about more or less fixed positions. Let me see if I can pull up this website for you so you can get a view of what happens. Actually, that PHET simulation would also be good. Okay. So you go to phet.colorado.edu. Physical states of matter. Let's look for chemistry. States of matter. And you've seen this animation before. Let's just look at it again. All right. And again, if they're too close together, they have very strong repulsions. Okay, and if they're very far away, these distances right here, this is beyond 1 nanometer. There's minimal interaction between them. Okay, if you remember this animation, we showed this earlier. You can look at the forces. See, so at very far distances, minimal interaction. At intermediate distances, you have these strong attractive forces. Okay, the yellow arrows here, and when they get too close together, they strongly repel. So that's why in a solid, they're as close as possible. They can't squeeze them any further. Okay, if you heat your atoms, you give them enough energy to spread out, to overcome those forces of attraction. And so you can see there's more freedom of movement as you go from solid to liquid and to gas. And so when they have enough energy to separate, then you get a gaseous sample of matter. Okay? Right. And these are other websites you can look at for animations of solids, liquids, and gas. Okay? So liquids are also incompressible, just like solids, and they're also as closely packed as possible, just like in solids. And the way you explain melting is, you give it, when you're heating your solid, you're eventually giving your particles enough energy to be able to move better and overcome the attractive forces that are keeping them together, but not enough for them to move about independently. And from an atomic perspective, a gas is compressible because on average they're very, very far apart from each other. There's a lot of empty space between the particles, and they're more or less free to move about. They have enough energy to overcome the attractive forces among them, and so they just fill up the entire container. Okay? So vaporization and sublimation is simply giving, they're endothermic processes, right? So basically what you're doing is when you're heating a solid or your liquid, you're giving your particles more energy, and when you give them more energy, what happens? Right here, if you look at your interaction potential, if you have, let's say, particles down here that are trapped in this potential, well, if you give them enough energy, then they'll have enough energy to separate. So if your energy goes up right there, then they'll have enough energy to be able to separate from each other, and they're not gonna get stuck. All right. So that's classification. That's the atomic interpretation of the classification. And like I said, for phase changes, basically what happens there is you're giving energy to your particles to overcome the forces of attraction that would allow them to move apart when you're changing from a solid to a liquid and liquid to a gas. Okay? Heating allows your particles to gain energy from more energetic particles. That would be the particles in the surroundings, the flame. Okay? So the particles in your flame, what you have in your flame here, okay? These are just high energy atoms, high energy particles. And what they do is what happens there is you have random collisions between those particles and your sample, and so you get a transfer of kinetic energy, okay, or thermal energy. Kinetic energy at the atomic level, we call that thermal energy. So redistribution of kinetic energy at the atomic level, due to random collisions. That's what we call heat transfer at the atomic level. All right. Now, one thing you do need to know is that attractive forces among molecules are easier to overcome than attractive forces among atoms in a molecule. The fact that atoms are bonded in a molecule tells you that the potential well for those atoms are very deep, and so it will require much more energy to separate them. So, for example, in a CH4 molecule, okay, if you have a pair of CH4 molecules, the well depth between them is quite kind of shallow. Okay. Oops, sorry. Let me redo this. Actually, I might have. So your potential well would be a very shallow well, whereas the potential between carbon and hydrogen within that CH4 molecule, your CH4 molecule has this structure. You've got 4 CH bonds. The potential well for this would be way deeper. It would be, something that looks like that. So it takes more energy to break those CH bonds as opposed to the energy needed to separate a pair of molecules. Let's continue. So here's a clicker question. In the figure below, which process best represents the vaporization of liquid nitrogen? So if you have nitrogen turning from a liquid into a gas, what happens? Is it best represented by process A or process B? This would be a clicker question. A. Okay. Nitrogen molecules, when they turn into a gas, okay, it's very easy to separate these molecules from each other, but it's going to require a lot of energy to actually split up these molecules into atoms. So what happens when liquid nitrogen vaporizes is this one. Okay? In a simple phase change where you have a solid or liquid turning into a gas, the molecules remain intact. Okay? It takes a lot of energy, way more energy than normal, to cause bonds to break. Okay, so when bonds break, you have what's called a chemical change. It takes those require much higher energies. Okay, so let me give you another example. What happens to water molecules? Let's say this is a water molecule and this is another water molecule. Okay, when water vaporizes, what happens? Does it give you, oops, sorry. There's another water molecule there, and another water molecule here. Oh, wrong color. Does it give you that? So that's going to be A. Or does it give you this? does it end up giving you? So is it A or B? Let's do another clicker question. Which one best represents the vaporization of liquid water? Conversion of liquid water to gaseous water. Here, where the molecules separate without breaking apart, or here where the molecules break apart into atoms. So what's the answer? When liquid water changes into steam, what's happening at the atomic level? A, very good. Okay, so in simple phase changes, molecules remain intact, no bonds are broken, no bonds are formed. It takes much more energy to actually break bonds. Okay, all right. Now, there is a fourth and fifth physical state of matter, which we're not going to go into because these are really cases where you're dealing with extremes. At very high temperature, you can get all your atoms to ionize, so your electrons can be ionized, and so you have a gas. It's basically an ionic gas, okay? Gaseous ions. So that's called a plasma. And that happens at very high temperature. If you're interested in that, there's that website right there where you can get more information. And then when you have very, very low temperatures, reaching near absolute zero, okay, you have what is known as a Bose-Einstein condensate, and you get some weird behavior there from atoms. And so there's a nice website on that from PBS that you can look at, okay? All right. So let's do a few clicker questions. Which of the following for which of the following are the atoms on average farthest from each other? A, air, B, gasoline, or C, copper wire? Okay. Air, very good. This is a gas, right? Gasoline is a liquid. Copper wire is a solid. So the correct answer is A. Good. Let's look at this one. For which physical state is the motion of water molecules most restricted? A, in ice, solid, B, in liquid water, or C, in steam, gaseous water? Most restricted motion. Okay, so looks like we're getting that. Most restricted in a solid. Okay, that's why solid tends to hold its shape. Okay. What physical state of matter is being described by the following phrase? Particles are as close to one another as possible and unable to move. Is it A, solid, B, liquid, C, gas, or D, none of these? Okay, so what's a popular answer for this? A is a popular answer. Okay, let me show you the, okay, I think I'm getting an echo from your mic. Let me show you the molecular view of what's happening in a solid, liquid, and gas again. Okay, I'm going to turn this to a solid. All right, here's a solid, okay, and a gas and a liquid. So as close as possible, right? So they are as close as possible, but are they unable to move? They're still moving. They're vibrating about more or less fixed positions. Their movement is restricted, but in a solid, they're still able to move. So the answer would be D. Okay? So I know this seems tricky, but this is what I'm trying to emphasize, that when in a solid, the atoms are still moving, even at very, very low temperature, even close to absolute zero. In fact, the movement gets really weird when you get very close to absolute zero temperature. Okay? And you get that Bose-Einstein condensate. All right. Let's look at this one. Consider the pictorial representation here for a change of physical state at the molecular level. The picture best represents which of these changes: evaporation, melting, sublimation, or condensation. A, B, C, or D. Okay. Looks like we have a close to 50-50 split. 7 people said C, and 5 people said D. All right, what's happening here? Far apart, right? Close together. So this might be a gas, right? And close together would be a liquid or a solid. So let's see if we can retake the poll and we can have a change of answers. All D, very good. Condensation. Okay. Sublimation is from a solid directly into a gas. So gas to liquid or solid, that's either condensation or the opposite of sublimation, which would be called deposition. All right. So now let's talk about classification of matter by composition. Most of the samples of matter that you find in nature are mixtures of what we would call substances. So they are mixtures, okay? If you have a sample that's made up of one substance, okay, this thing that makes up the matter in nature called substances, it's a mixture of substances. If you have a sample that's just made up of one substance, you call it a pure substance, and they are rare in nature. What you find in nature are mixtures of substances. If you do find samples of pure substances, chances are you're probably in a chemistry lab or something. So because these are things that you make in the lab, you separate matter into components, okay, and you get to a point where the component you have is called a pure substance. Okay, now a substance can be classified into two kinds. It's either a pure element, and that means you cannot separate it into two or more distinct components. It's just one pure, it's just You cannot separate it further. Okay, so that's called an element, and it can be also classified as a compound if you can have a substance that you can further separate into two or more elements. The question is exactly what's a substance? How do we define a substance? Well, if you have a pure substance, okay, typically if you look at it, it's going to be homogeneous. Homogeneous simply means the properties are uniform throughout. Regardless of what part of the sample you're looking at, the characteristics or the properties of that sample is the same, regardless of which part of it you're looking at or testing. Okay. The only exception is when it's undergoing a physical state, a change in physical state, in which case you might see one part's a solid, the other part's a liquid if it's melting, for example. Okay. So the homogeneous sample of matter has uniform properties throughout. Pure water. Water is an example of a substance. If you have a pure sample of water, you have a sample that has nothing but water in it, then it will be a homogeneous liquid at room temperature. Below 0 degrees Celsius, it will be a pure solid. It's a homogeneous solid, and we call that ice. But at 0 degrees Celsius, you can have ice and liquid water. So what the sample you have at that point is called heterogeneous, even though it's still a pure substance. It's still pure water. Most mixtures, on the other hand, that you find in nature are heterogeneous, okay? That means you can obviously tell one part from the other. So you can obviously tell that it's made up of more than one part. But there are some mixtures that are also homogeneous, and those are called solutions. And I still haven't answered my question. How can you tell if you're dealing with a pure substance? Experimentally, what you do in the lab is if you have a solid, you try to melt it. And while it's melting, its temperature will remain constant, okay, until everything's melted. So we say it has a sharp melting point. And if you keep heating it, eventually you're going to turn it into a gas. And so if this is heating time right here, and you plot temperature, okay, while it's melting, let me fix this. So if it was a solid, okay, temperature is gonna go up while you're heating it, but when it starts melting, the temperature is gonna level off. So we say it has a sharp melting point. Once everything's melted, that's only the time when the temperature starts to go up. So the temperature of the liquid starts to go up, and then eventually it starts to boil, and while it's boiling, the temperature remains constant again. When everything's turned to a gas, that's the only time it starts to heat up to the temperature. The temperature goes up again, okay? So it has a sharp melting point and a sharp boiling point. Now, if you have a mixture, okay, then this is not going to be flat. The melting point, melting temperature and the boiling temperature is not going to be flat. Now, what would we consider as a constant temperature? In the lab, for practical purposes, if the temperature stays within 1 to 2 degrees while it's melting or boiling, then we say that it has a sharp melting point or a sharp boiling point. Let me show you an animation of that. Let's do a search for Cam Davidson heating curve from Davidson College. Here's an animation. All right. Alright, so in this animation, imagine that this blue thing right here is a solid, okay? And I'm going to heat it. I'm going to be plotting temperature versus time as I'm heating it. What I'll do is I press that button that says heat, and when I'm heating it, what happens? The temperature is going up. That's the red curve right there. Now look, it's melting, okay? You're seeing this red. It's being shown here as that blue turning into red. Okay, so that's melting. It's turning into a liquid. While it's melting, the temperatures remain staying constant. If I continue heating it, what happens is, okay, you'll notice you're getting more red, you're getting more liquid, you're getting more solid turning into a liquid. Eventually, all the solids melted. Okay, so what you have there is now a liquid. This is now a liquid. So if I continue heating that liquid, its temperature is going to start to rise. And once that liquid starts to boil, turns to a gas. Okay, now you see that yellow, okay, part right there. So this is now the yellow part right here represents a gas. While it's boiling, the temperature is staying constant. Okay. And notice what's happening here. When a liquid turns to a gas, look what happened to the volume. When you're changing from a liquid to a gas, there's a big increase in the volume. Why is that? At the atomic level, remember we said in a liquid and a solid, they're as close as possible. When you turn that into a gas, the molecules spread out, and so the sample will occupy a much larger volume when you turn it from a liquid into a gas. Okay, if you continue heating, okay, while you still have liquid and gas in there, and the temperature remains constant, so that's your boiling point. If I continue heating it, eventually all of my liquid turns to a gas, and then the temperature of the gas will start to rise. Okay, so now everything's a gas, and your temperature's gone up over there. Okay? So that is how you can determine whether you have a pure substance if it has a sharp melting point and a sharp boiling point. Now, what would happen if this wasn't a pure substance? What would happen is if this solid was contaminated, it would actually melt starting at a temperature below the pure melting point, and it will continue to melt. Okay, temperature will be rising as it melts. Same thing, while it's boiling, it will start boiling at a higher temperature, and the temperature will keep rising as you're boiling it. So that would be a mixture. Okay, you would say then that whatever substance you have, even if you have a lot of it there, it's probably not pure, it's contaminated with something else. All right. Now, mixtures can be classified as homogeneous, in which case they're called solutions. An example of a homogeneous mixture would be salt water. If you put some salt in water, okay, what you'll find is that you stir it, your salt will disperse in the water, and you can't tell by just looking where the salt is. It's evenly dispersed throughout the water, and so you have a homogeneous mixture. That's called a solution. Brass solution doesn't have to be a liquid. Okay, brass is an example of a solid solution. Okay, that's two metallic elements that are mixed evenly, and you have a solution. Okay, air is also a solution. It's a mixture of nitrogen molecules and O2 molecules and a few other gases. There's carbon dioxide, there's water vapor. So air is a solution, except if it's dust free. If you can tell the dust in your air, you can tell that there's dust in your air, then you're dealing with a heterogeneous mixture. Okay, coarse mixtures are mixtures that are obviously heterogeneous by just looking at it. You can tell that there's more than one component there. For example, a salad would be an example of a coarse mixture. Now, somewhere between solutions and coarse mixtures, you have what are known as colloids and suspensions. These are classified as heterogeneous mixtures, just like coarse mixtures. But unlike the coarse mixtures, a colloid and a suspension, you have one major component and you've got particles of the other components evenly dispersed. So you might have a liquid or a gas, like water or air, and then you've got particles dispersed on it, in it. Okay, so for example, if you've got dust dispersed in your air, that's really a suspension. If you could pick out the dust by just looking at it. Okay, so in a suspension, you have fine particles that are large enough for you to see with an unaided eye. By just looking at it, you can tell there are particles moving about and being dispersed in your mixture. And so an example of a suspension, okay, would be something like medicine that has a shake well before using label on notice on the label. Okay, these fine particles are usually large enough that they settle on standing. So if you just let it sit, those fine particles are going to settle to the bottom. So, you know, if you have dust in your air, that's a suspension of solid in a gas. If you give it time, those dust is going to settle to the floor. Okay. Same thing with suspension medicine that has label on the bottle that says shake well before using. The reason that label is there is because the medicine that's dispersed in your the solids that's dispersed in the liquid in that medicine would settle on standing. Okay. Colloids are similar to suspensions, except that the particles are so fine that you can only see them by shining light through it. Okay, without just with the unaided eye, you won't be able to see the particles. So this effect, this is known as the Tyndall effect. When you shine light on something and you see the particles, that's called the Tyndall effect. What happens there is light bounces off those particles, and you see it's called Tyndall effect is what we would call light scattering by fine particles. So these particles are so fine that they don't settle on standing. Okay, so an example would be fog. Now, there isn't a fixed boundary between what would be considered a colloid and a suspension, so you could get into some gray areas there. But these are just some of the general classifications of mixtures. All right. Now, a compound, we said, is a pure substance that can be broken up into two or more components. Okay. So how is that different from something that's simply a mixture of two elements? Well, a mixture of elements will not behave like a pure substance. So you can do your typical test in the lab. Simply test for the melting point and the boiling point. Okay? And a mixture of elements will also tend to resemble the properties of the elements that it contains. A compound typically looks very different behaves very differently from the elements that make it up. So for example, water is an example of a compound. Okay? Water is a compound. It's made up of hydrogen and oxygen. Pure hydrogen, pure oxygen, under ordinary conditions, they are gases. But if you have water, which is made of hydrogen and oxygen, water is not a gas under ordinary condition. Okay, so water is a compound. You can break it down into hydrogen and oxygen, but it doesn't resemble hydrogen or oxygen at all. It's a completely different substance. One characteristic of compounds is that they have what's called a definite composition. So the law of definite composition says that if you have a sample, a pure substance, and that can be broken down into elements. In other words, if you have a compound, it has a definite composition. So in the case of water, for example, okay, it's a compound made up of hydrogen and oxygen. If you break it down, okay, the mass percent of hydrogen is always going to be 11.21%, and it's always going to be 88.79% oxygen by mass. If I have 100 grams of water, I will always get, if I were to break it down, I'm going to get 11.21 grams of hydrogen, and I'm going to get 88.79 grams of oxygen, regardless of how I made the water, regardless of whether the water came from Siberia or China. It's still, if it's pure water, it will always give me a well-defined proportion of the elements if I break it down. Okay? Hydrogen peroxide, another compound of hydrogen and oxygen. If you break it down, it will always be 5.94% hydrogen, and it will always be 94.06% oxygen. Okay, so water and hydrogen peroxide, we say, are two compounds of hydrogen and oxygen, but they're different substances. Pure water is a different substance, hydrogen peroxide is a different substance, even though they're both made up of hydrogen and oxygen. And neither one of them is a mixture. If it's in pure form, you can't call them a mixture of hydrogen and oxygen. They are a compound because they have properties or characteristics that are different from water, from hydrogen and the oxygen. All right, so here's an example of a question that tests whether you understand the concept of definite composition. Let's say the percentage by mass of chlorine percentage of chlorine by mass in a compound is 25%. What's the percentage of chlorine in a 20-gram sample of this compound? Okay. So I have a 10-gram sample of a compound. I find out that it's 25% chlorine by mass. If I have a 20-gram sample of this compound, what's the percentage of chlorine in this sample? What would be the answer? Is it 5, 10, or 20? Let's see. Okay, it's 25%, right, in a 10-gram sample. That means in any sample, when we say it's a law of definite composition, the law of definite composition says any sample of this compound will be 25% chlorine. Just like when we talked about water earlier, any sample of water is 11.21% hydrogen, 88.79% oxygen. So when we say that a compound is 25% chlorine, it doesn't matter if it's 10 grams, 20 grams, 50 grams, 100 grams, it's still going to be 25% chlorine if you're dealing with the same compound. Any sample of that compound, we say, has a, that's what we mean when we say the compound has a definite composition. The percentage of each element by mass is going to be the same. Here's another example. Let's say you have a 16-gram sample of a compound, okay? If you break it down, it gives you 12 grams carbon and 4 grams hydrogen. Okay? So what's the percentage of carbon here in this compound? How do you take a percentage? You take the part divided by the whole, so 12 out of 16, and then you multiply by 100%, right? So what's 12 out of 16? 12 divided by 16 is how much? That's 3/4, so that's 0.75 times 100%. Okay, so 3/4, or let me say it's 75% carbon. Okay? Oops. So that means any sample of this compound is going to be 75% carbon, and you should be able to show that the percentage of hydrogen in this compound is 4 grams out of 16 grams times 100%, and that's going to be 25% hydrogen. Any sample of this compound is going to be 25% hydrogen by mass. So the question is, what's the mass of this sample? What mass of this compound will contain 24 grams carbon? The way you'd figure that out is you say, okay, it's got how much? 24 grams carbon. So we say 24 grams carbon is 75% of the mass, right? The total mass. Or in math, you say 25 is, in math, is equals 75% of something. We're looking for the total mass. We don't know what it is, so we're going to call that x. 75% of x is 0.75 times x. Okay, so you can see that x, divide both sides by 0.75. Did I say 25 or 24? I'm sorry, 24, right? It should be 24. 24 grams is 0.75 times x. So divide both sides by 0.75. 0.75 cancels out, and that gives us x equals 32 grams. And you can see that, you can verify 24 out of 32. Okay, so divide by 8, so that's reduced to lowest terms. That's 3/4. So that's 75%. Okay? All right. So that's how you'd figure that out. You just need, that's what definite composition means. Another way you could have worked this question out was this. You could have said, definite composition simply means that the amounts are directly proportional. So in other words, I can say, okay, I can use conversion factors here. I can say 24 grams, because what it's saying is if I have like 32 grams, then I'm going to get 24 grams of that and 8 grams of that. In fact, you could just have uh, done that, just done that in your head. You could say, okay, if I have 24 grams carbon, then I must have twice as much of the compound, 32 grams. Another way you could have done this is you could say 24 grams carbon times, you can use this information as a conversion factor. You're going to say 16 grams of compound, CPD is compound abbreviation, okay, for 12 grams of carbon. And that's still going to give you the same answer, 32 grams of your compound. So that's another way of doing the problem, okay? So how much hydrogen is in this sample? Well, if it's 24 grams carbon, then you just subtract that from 32, you get your hydrogen. Or another way you could have done that is you could say 24 grams of carbon times your conversion factor. In this case, you say you have 8 grams of hydrogen for 24 grams, I'm sorry, 4 grams of hydrogen right here. 4 grams of hydrogen for 12 grams of carbon. So that should give you 24 divided by 12 is 2. 2 times 4 is 8. 8 grams of hydrogen. Okay? So you can use conversion factors in this case. And the reason you can use conversion factors is because these things are what we would call directly proportional quantities. You got 3 times as much compound, you're going to get 3 times as much carbon, you're going to get 3 times as much hydrogen. You got 5 times as much carbon, then that means you're going to have 5 times as much hydrogen, and you'll have 5 times as much of the compound. That's what we mean by definite composition. In either any of these cases, the percentage of each element is going to be the same in the compound. What's the percent of carbon here? 12 out of 16, 75%. 24 out of 32, that's 75%. All right. All right. Let's look at the atomic view of the differences between elements, compounds, and mixtures. We say we have a pure sample of an element if it's made up of only one kind of atom. Now, compounds can be broken up into 2 or more elements, so we say it must have at least 2 kinds of atoms in there. But we say the reason a compound has a well-defined set of properties, unlike a mixture, is because the atoms are organized in a well-defined manner. For example, so in other words, water, for example, we can assign a formula to a compound. So it's got a definite composition. So water is H2O. That means there's 2 hydrogen atoms for every oxygen atom you find in a sample of water. Okay, so that would be the atomic interpretation. It's made up of only one kind of molecule, or if it's made up of ions, that means it's made up of only one kind of cation and only one kind of anion. So here's an example. Which of these figures represent a compound if the red circles and the blue squares represent different kinds of atoms? So let's make this a clicker question. A, B, or C? Which one represents a compound? Which one represents a compound? Very good. Okay. A would be an element. What would B be called? This would be a mixture of two elements, right? And C would be a compound. Well-defined composition. All right. Let's look at this clicker question. Consider the pictorial representation here of the molecular composition of a mixture. This is obviously a mixture. Assuming your filled circles are carbon, so this black circle right here is carbon, and the unfilled squares are oxygen, so that would be oxygen right there. Okay. And we can say that this figure represents a mixture of an element and two compounds, B, two elements and a compound, C, three compounds, or D, two elements. Okay, 3A, 4B, 6C. All right, let's see. This is just made up of one kind of atom, so a collection of these would be an element, right? If that's all you had, then you would have a sample of an element, a pure element. But this is a mixture of this element and, okay, these molecules are made up of two elements, and they're organized in the same way. So this would be a compound, same compound, molecules of the same compound. And in fact, the formula for the element is O2, right? The unfilled squares are oxygen. So this is an element O2. The compound here is made up of molecules consisting of one carbon atom and one oxygen atom. So that's carbon monoxide. And this other one here, two oxygens and a carbon. Okay, let me color code that. Two oxygens and a carbon. That's a compound called carbon dioxide, CO2. So the answer here is an element and two compounds. Okay, your element is O2. Your two compounds are carbon dioxide and carbon monoxide. All right. Few more clicker questions. A naturally occurring sample of matter most likely consists of a single element, a single compound, a mixture, or a pure substance. Let's see if you remember. Very good. In nature, most of the samples of matter you find are mixtures of substances. Substances can be either elements or compounds. All right. What type of matter cannot be separated into two or more distinct components? Element, compound, mixture, or pure substance? Okay. Cannot be separated, that means element. Compound, you can still separate into two or more elements. Okay. So if you can't separate it into two or more distinct components, you're dealing with an element. All right. A sample of matter is heated, found to start melting at 75 degrees. While melting, the sample temperature continues to rise to about 85 degrees. This sample of matter is most likely an element, a compound, or a mixture. Very good. Mixture. Okay. If you have a pure compound or a pure element, it's going to have a sharp melting point. Temperature will stay within 1 or 2 degrees while it's melting. Okay. Here's a practical question in the lab. Let's say you have three samples, A, B, and C. They appear to be identical. Okay. Keyword there is they appear to be identical. Sample A is found to melt sharply at 122 degrees. If you mix, okay, mix being simply putting them together, okay. It's samples A and B, you found that it now melts from 115 to 120. While if you mix A and C, so A and B, the melting goes from 115 to 120. If you put together A and C, okay, you find that it melts at 122 still. So which of these is true? A and B is the same substance. A and C are different substances. B and C will have a sharp melting point, or D, none of the above. This is actually how you would determine whether something is pure in the lab or not. You mix it with something that you know. And see the effect on the melting point. Popular answer is B. Okay, let's see what happens. If A and B melts from 115 to 120, then A and B are not identical, right? Otherwise, if A and B are the same sample, same compound, then A and B should melt at 122. So which one can you eliminate? Choice A is wrong, right? What about A and C? If you mix A and C, it still might melt at 122. So A and C must be identical. So A and C must be identical. So choice B is also wrong. So A and C are the same. How about B and C? Are B and C the same? If A and C are the same and A and B are not the same, what does that tell you about B and C? Are they the same? They're not the same, right? So you say A is the same as C, neither one of them is the same as B. So if I were to put together B and C, I'm not going to have a sharp melting point. So C is wrong too. The correct answer is D, none of the above. Okay? Okay, here's another question. 25-gram sample of a compound is found to be 24% chlorine by mass. What's the percentage of chlorine in a 50-gram sample? If you have twice as much sample, what's the percentage of chlorine? Is it 24, 48, 12, or it depends on where the sample came from? It's a popular answer. Very good. Still 24%. That's what we mean by law of definite composition. All right, next one. 25-gram sample is 24% chlorine by mass. How much chlorine is in a 50-gram sample? 24 grams, 48 grams, or 12 grams? See? Okay. Definite composition, so whatever your sample is, it's still going to be 24% chlorine, right? So 24% of whatever sample you have, in this case 50 grams, 24% of 50 grams is going to be 12 grams. Very good. So the way you do this in math is you say it's 0.24 times 50.0 grams, okay? Which is going to be 12 grams. Here's a question. 17-gram sample of a compound contains 14 grams nitrogen, 3 grams hydrogen. Okay, so 14 grams nitrogen, 3 grams hydrogen from a 17-gram sample. That's what it breaks down to. How much hydrogen does a 34-gram sample contain? So if you have 34 grams of the compound, how much hydrogen would you have in that compound? Think about it this way. 34 is twice as much as 17. Very good. Or if you want to work it out using conversion factor, you can say 24 grams of compound times 3 grams of hydrogen for 17 grams of compound. Okay, grams cancel out. 34 times 3 over 17, that should give you 6 grams. Okay, good. 32-gram sample. Okay, this is more of the same, so I think we've had enough practice for this. I'll give you more practice in the homework for this one. Okay. All right, I think that's it for today. Okay, hold up.